As we're looking at logarithms, I want to make sure that we all understand, have a really good understanding of what logarithms actually give us. Because guys, if you don't understand what we're talking about today, then the rest of our time talking about logarithms is going to kind of be, you're going to kind of be semi-lost. All right, you really have to understand what logarithms are in order to really understand how to use them, okay? But first of all, let's look at how this is defined. We have this equation y equals log, and then you have the little a down here, log base a is how we'd read that, of x. Understand the logarithm is a function. It's just like if you have the sine of an angle or the tangent of an angle. We have the square root of something. These are all functions. Here we have a logarithm function. Okay? Now, notice a couple of things here. First, notice what a can be. A, just like an exponential, has to be positive. It's got to be greater than 0. And also, a cannot be 1. Alright, so this is where we can start seeing the relationship between logarithms and exponentials. Okay? Also, notice the domain. The domain for what x can be, x has to be a positive value. Alright, so x can't be 0, x cannot be any negative number. So, what really is a logarithmic function? Well, let's take a look at this. First of all, understand that when you are taking the log of something, you are finding an exponent. You're trying to find the exponent. And you'll notice right here it has x equals a to the y. We're trying to get that value y. Okay? That's what the logarithm gives us, is the exponent. Okay? So make sure you understand that. We're dealing with exponents here. The logarithm is a function that takes a base, so the base a, and a value, that's what the x is, and it returns the exponent of that base, the exponent of that base that will give you that value, in this case, x. Right? So as you're reading these, okay, as you're reading these, think of it this way. This statement right here says that x is the exponent of, what's our base? 2, that will give us a value of 8. Okay? This is how you need to think of this. X is the exponent of 2 that will give us 8. Logically, this is the equation we're dealing with. 2 to what power equals 8? And of course, you guys can figure out that that's 3. 2 times 2 is 4, times 2 is 8. Does anyone have any questions so far? Now, as you can see here, here is another case where you can see how the exponentials and the logarithms are related to each other. Really, one is just an interpretation of the other. So, in fact, these are related in a way where the exponential and the logarithm, we can actually say are inverses of each other. Calvin, did you? So let's look at what we mean by that. An exponential and a logarithm with the same bases, this is the important part, are inverses of each other. Okay? So here we have the exponential function with a base of b. Okay? The inverse function is going to be a log base b. Alright? So when we have an equation like this, 10 to the x power equals 25, when we're trying to solve that equation, we need to think, okay, what's the base of my exponential? What is it?
10.
It's 10. So to undo, to use an inverse operation, I would need to take a log base 10 of both sides. Okay? The log base 10. And what this does then, notice the log of the exponential function takes us back to x. That's our definition of an inverse function. Okay? So we can say that the log cancels out the exponential and we're left with just the exponent x. And then this we can use our calculator for. The log base 10 of 25. Okay? Now, you can't do any log on your calculators. Okay? You can only do certain logs on your calculators. When you see the log button here, that is built in to have a base of 10. Okay, so we can actually evaluate this one. The log of 25, that equals 1.3979, so we'll do 2 decimal places, 1.40. Okay? So, our calculator can do that one. And that's actually one of 2 that our calculator can do. Okay? And this one with a base of 10 is known as our common log. That's a term you ought to know. Okay? Alright? You guys figure out how to do the log on your calculator? Did you find it on the Inspire? Or is that an 84? You got the 84? Okay? Those of you with the Inspire, did you find the log? With the Inspire, you actually have a little bit of an advantage because it'll let you type in whatever base you want.
We can indeed
do that on the 84 too.
You can do it on the 84? Oh, that's nice. For those of you with the 83 or a non-updated 84, not all the 84s will let you do it, so. Now, the other one though that any calculator will let you do, any scientific calculator, is a base of e. Okay, we said that e was the base of the natural exponential function. We looked at that yesterday. Okay, and a log with a base of e is the natural log, and it's as ln. Okay, so on our calculator, right below the log button is the ln buttons. We have the natural log. Okay. If I had an equation, say like this, you know, e to what power would equal, say, 7? I'm thinking, okay, I have an exponential, its base is e, so I need to take the log base e of both sides. This will undo and leave me with just an x, and then the natural log of 7 is what? 1.95? Alright. 1.95. Okay? Any questions here? Alright. So let's think a little bit more about these ones here. Okay? Some of these, though, you can do in your head. Alright, if you think about what exponent of 10 will give us 10,000? 4. Okay, we've got 4 zeros there. If you weren't sure, you could do the log base 10 of 10,000. Okay, and that'll get you your 4. Okay. Understand that your exponents can be negative, though. Here I have 10 to the x is 1 over 1,000. So obviously to get a fraction we need a negative exponent. So what would x have to be in this case? Yeah, negative 3. Okay? We're taking the log of 1 over 1,000, so we're going to get a negative 3. Okay? Keep this stuff in mind, not just with tens, but with anything. If you want to end up with a number that's smaller than your base, obviously you have to have a fraction. Okay? You have to be doing some kind of a reciprocal in there, so you're going to have a negative result when you plug it into your log. Okay? Again, we can also use e as well. Okay? This doesn't just work, though, when we're solving equations that are exponential to begin with. We can also use this same concept when we're solving logarithmic equations. Let's say we have the log base 2 of let's do that. Log base 2 of 16 equals x. If we're just trying to find that, okay, we could rewrite this using that concept of the inverse operation. The inverse of a log base 2 is an exponential with a base of 2, right? So if we made both of these 2 to the power, okay, this exponential will cancel out the log, and what's left on the left-hand side? Just a 16. Okay? So then we could say, okay, well, 2 to what power is going to give us 16? The 4th. Right? You can also do this if you have one where the x is inside the log. Let's say we've got a log base 3 of x equals 4. Okay? The log base 3 of x equals 4. Well, the inverse of a log base 3 is what?
3 to the 4th power.
An exponential of the base 3. So yeah, we're going to have 3 to the 4th power. We take both sides and we make those the exponent of 3. Okay? That will undo the logarithm, leaving us with just an x. And now we have 3 to the 4th, and that's 81. Okay? So are there any questions on how we're using these? You need to really make sure you understand how to solve the equations, whether you're starting with an exponential or starting with a logarithm. Mm-hmm.
We should do the blue one the second step.
For this?
Yeah.
Basically, I just took both sides of the equation. I saw the base was 2, so I made that the base on both sides. And I just took what was here and made that the exponent of 2. if these are equal, then if I raise something to those powers, it should stay equal, right? So,
How do you get 16?
what?
How do you get 16?
Because here this exponential with a base of 2 and the logarithm with the base of 2 are inverses of each other. That's what we were saying, right here. Exponentials and logarithms with the same base are inverses. So when you do the log of an exponential, or the other way around, an exponential of a logarithm, it will take you back to just what's inside here. Okay? They undo each other, you could say. And it's the same concept that we use when we have an x plus 2 and we subtract 2 from both sides of an equation. They're just inverse operations, or inverse functions. Okay? Alright, so let's tie this together with what we looked at yesterday. Let's say we got this investment. I'm going to invest $12,500 at 7% interest compounded continuously. But I know how much I want to end up with. Okay? How long will it take me to have $20,000? Okay? Let's make sure everyone's on the right formula, and then I'll let you guys try this. What formula should we be using here?
A equals P times E to the power of T.
Oh, so it was.
RT.
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 There we go, good. The amount at a given time t equals P times E to the RT. Alright, so take that. We're trying to solve for t, okay? Take that, set up your formula. If you're having trouble with it, ask a friend or ask me. And try to solve for the time. Don't round until you get to the end. If you can't remember what the variables stand for, look back in your notes.
It would be e to the 0.07t. 0.07 times t would be in the exponent. Yeah, yes, that's exactly right. difference of r.
Yeah.
So now,
Log?
yes, then then you've got a base of e for your exponential, so what kind of log are you gonna use?
E.
The log base e, yeah. Oh. Now, this, oh, make sure you're careful with your order of operations. You can't, the 12,000 is not being raised to the 0.07 power by the t power. No, so what you would wanna do is divide by 12,000 first. So you have e to the, that power.
Second.
Yeah, now, if this was your equation, that is how you would solve it, but you don't wanna do that part.
Alright, I think most have gotten at least to this point here, okay? Be careful when you set up your formula, don't overthink. Just plug in the values, identify the values, and plug them in exactly where they're supposed to go, okay? So this right here is your amount at time t. We don't know what the time is yet. Alright, this right here is our principal. This right here is the rate, and we would write it as a decimal 0.07, okay? So, this says it's p times e to the power of r times t. So that's why we plug it in this way, okay? Now, only the e is being raised to this power, not the 12,500. So we want to get rid of that. We need to get rid of that 12,500 before we can take a logarithm. Okay? So what we'll do here is we'll divide by 12,500, and that's where we get the 1.6. Alright? Is everyone with me up to that point? Everyone understand?
Yeah.
Okay. So now, what do we do at this point? Good, the natural log. We're going to take the natural log of both sides of the equation. This we just punch into our calculators. This, when I take the natural log, what's left over? Good, the 0.07 t. When you undo that exponential using the logarithm, all that's left is your exponent. Okay? And then we have natural log of 1.6. Right. Now, when you do this, by the way, do not round at this point. If you want to punch it into your calculator, that's great, but use that whole value and then finish it off by dividing by the 0.07, and you get t equal to
6.714.
okay, 6.714. So we'll round to two decimal places, make it 6.71. Okay. And what's our unit of time here?
Years.
Okay. How do we know it's years?
Because it's less than the equation.
Okay. That's what our equation usually accounts for.
Oh, because this is compound continuously? No.
We had the 0.07 and it's like r over n, so n had to equal 1.
No, it is related to 0.07. That interest rate is an annual rate.
Yeah.
Okay? Anytime you see an interest rate, unless they tell you specifically we're earning this much per month or something, it's an annual rate. Okay? So we are in years. Technically, you could, if you had an interest rate that was, say, a monthly rate, you could do your time in months. Alright? We don't normally do that, but as long as your rate and time have the same unit of time, or in terms of the same units of time, you can do that. This is how we could use this formula, remember, in other contexts that aren't money, like with bacterial growth, and it might be in a matter of hours or something like that. As long as your percent is in terms of the hour, that's okay. You just have to make sure your units of time match up. All right, I gave you a few to try here for some practice. Some of these, okay, notice they give you an example what they want you to do. They're not even really concerned with you solving it because there aren't any variables. They just want you to get used to writing a logarithm as an exponential. Okay, that's what I want you to do as well. All right, same thing on the bottom. We have natural logs doing something similar. Okay. And then there's a few applications, okay, some just equation solving, all right, and then number 96 is a home mortgage, okay. You know what, why do I have 39 and 42 in there? Omit 39 and 41. So just do this to 37. Right now. All right.